right, good afternoon, everybody. I'll go ahead and introduce our speaker for today. Dr. Shanghong is an assistant professor in the Department of Statistics here at the University of South Carolina. She's also a member of the Carolina Autism and Neurodevelopment CAN Research Center and the Institute for Mind and Brain, INBRE. She earned a doctorate in biostatistics from Columbia University in 2019. Her research interests lie in the broad area of machine learning, network analysis, precision medicine, functional data analysis, causal inference, mediation analysis with neuroimaging and genetic biomarkers, and variable selection. Her work focuses on developing machine learning and generative models to address complex challenges in neuroimaging, neurological and mental health disorders, and public health. It's our pleasure to have her speak today on her topic. So I'm going to turn it over to you, Dr. G.
Okay. Thank you, Jaja and Becky, for inviting me to be here today. So today I'm going to talk about dynamic system for modeling disease progressing with temporal registration. Neurodegenerative disorders such as Alzheimer's disease, AD, are chronic conditions that affect millions of people worldwide. AD affects about 60 to 80% of the more than 50 million dementia cases globally. These disorders are characterized by progressive degeneration of neurons in the brain, leading to cognitive decline and motor dysfunction. Understanding the natural history of these diseases and predicting disease progression is crucial for developing effective early interventions. In particular, disease-modifying therapy may be more beneficial prior to clinical diagnosis. This figure compares symptomatic therapy and disease-modifying therapy. On the left, symptomatic therapy tends to temporal improvement, but patients continue to decline at the same rate as if untreated, so the underlying disease progression is not changed. In contrast, on the right, disease-modifying therapy reduces the rate of decline. The slope is flatter, which delays the progression over time. And it is crucial to identify the optimal timing to initiate intervention. Disease progressing models have been developed for cancer, cardiovascular disease, infectious disease, and ADs. However, there are several challenges in modeling disease progressing. Disease progressing often exhibits substantial between-subject variability. The trajectories may not follow a uniform pattern across patients. The heterogeneity may arise from multiple factors, such as genetic variations, environmental factors, or other unobserved variables. Another challenge is temporal heterogeneity, which is also referred to as time warping. AD may begin at different ages across individuals, which we call time shifts, and it may progress at different rates, meaning that trajectories may be stretched or compressed along the time axis. Moreover, available data typically represent only a short snapshot of long-term progressing. Temporal variability has been seen among individuals. This figure illustrates this idea conceptually. Individuals may follow a similar underlying disease curve, but their trajectories are shifted or scaled along the time axis. While on the right, this figure shows what we actually observed, misaligned trajectories. So a key modeling challenge is to reconstruct latent disease progressing timeline while accounting for subject variability. Next, I will briefly review existing disease progressing models, DPMs, DPMs aim to characterize dynamic changes in the long-term disease evolution. One of the most influential approaches for AD is sigmoid model. It assumes that biomarker trajectories follow an S-shaped curve. As shown here, the different biomarkers become abnormal at different stages of the disease. Each one follows a sigmoid-like pattern, with some markers change earlier and others later. However, this approach has several limitations. The sigmoid assumption may be overly restrictive and may not fully capture the complexity of disease dynamics. It also requires the identification of an appropriate temporal reference point. In addition, it fails to account for complex interactions between different markers. It models the disease trajectory for each marker separately, therefore limiting their abilities to simulate progressing scenarios that involve dynamic changes of multiple markers. An alternative and more flexible class of models is based on dynamic systems or ordinary differential equations, ODEs. ODEs directly model the rate of change. They can capture nonlinear disease dynamics and annul time-varying interactions among biomarkers. For example, how amyloid accumulation influences glucose metabolism. Another advantage of ODE-based model is that they are generative models. Once the system parameters are estimated, we can simulate full disease trajectories and evaluate intervention strategies by modifying system dynamics. For example, we introduce an amyloid-lowering therapy at different stages of the disease and compare their resulting trajectory, then identify the optimal timing. This flexibility makes ODE-based models particularly attractive for understanding complex and multi-marker disease progressing. Despite their advances, ODE-based models face challenges similar to other DPMs, including unknown origin of progressing, and we need to account for heterogeneity in the progressing timeline. To address temporal misalignment, curve registration methods are widely used to align individual trajectories via time warping functions. Functional data analysis techniques are widely applied, such as functional principal component analysis, square root slope function transform-based methods, and B-spline warping. These methods primarily address phase variation, the horizontal shifts. Warping functions typically do not directly incorporate subjects' covariates. By associating warping function with subjects' covariates, we can quantify how individual characteristics contribute to disease progressing. This allows us to identify subjects with a higher risk of rapid decline and may help inform personalized treatment strategies. Therefore, in this work, we develop a dynamic disease progressing model based on ODEs. We model disease evolution with progressing modifying effects, allow subject-specific initial conditions for individualized trajectories. We introduce a covariate-dependent temporal registration mechanism to align individuals to a common timeline. Our model provides flexibility in specifying the functional form of ODE dynamics, and we can predict and simulate future disease trajectories. So let me introduce our methods. First, I will describe a simple ODE-based progressing model that serves as a starting point. For each subject, we observe the measurements of multiple markers. They may from multimodality data. For example, amyloid, glucose metabolism, brain atrophy, and clinical scores. The observed measurements YI is modeled as a latent true disease process with random noise. The underlying disease progressing is governed by a system of ODE. The rate of change depends on the current state of disease, captured by function f. Each subject has subject-specific initial conditions, denoted as eta I0. For the time tau, without loss of genericity, we assume tau is between 0 and 1. The F is shared across individuals, which represents a standardized progressing mechanism. If the functional form of F is known, we will use a parametric ODE with the same functional form. If the functional form is unknown, we will model it by neural ODE. Individual heterogeneity may arise from different starting points of the disease trajectories. Therefore, we introduce subject-specific random initial condition. We assume it from a distribution. Specifically, we assume they are from the log normal distribution with mean mu0 and covariance sigma 0. So this allows individualized trajectories. So far, we assume a single mechanism to capture the disease dynamics. Now we allow for a structural change after an external event, such as the initiation of a progressing modifying treatment. Before the event time Ti, disease progresses according to one dynamic mechanism, F1. After the event time Ti, the dynamic switches to a different system, F2. Here, Ti is subject-specific. If Ti is 0, treatment is at the beginning of disease progressing. If Ti is 1, no treatment occurs. To make this more concrete, let's think about a parametric ODE system presented in A.B. Nanda's paper to model AD progressing. Before treatment, the disease dynamics is modeled by F1. Here, A1 and A2 are coefficient matrices, which capture the linear and nonlinear interactions among biomarkers. After treatment, the system is modified by a diagonal matrix gamma. F2 equals gamma F1. Its element gamma K represents the treatment effect on the case marker. For example, gamma amyloid equals 0.5 if some amyloid lowering intervention can reduce the accumulation rate by 50% on the amyloid biomarker. The simple ODE model assumes a common timeline across individuals. Therefore, it cannot fully capture between subject variation. In practice, subjects differ in when they enter the disease process and how quickly they progress. This leads to time shifts and time compression or expansion. Therefore, we need temporal alignment to reduce temporal variability across individuals and in turn to improve prediction performance. Therefore, we propose a temporally registered ODE model. We introduce a subject-specific time warping function HI, which maps internal time tau to observed time t. Here, Tmax is the maximum observational time. The HI is covariate-dependent. In the observation model, we use the inverse mapping function HI inverse to recover subject's internal time. We require HI inverse is monotonely increasing to ensure the identifiability of temporal realignment and impose boundary conditions so that every subject shares the same internal time scale. This figure illustrates the effect of temporal registration by simulated data. Panel A shows the observed trajectories over observational time. Subject 2, the purple line, progresses faster than subject 1, the orange line. Panel B shows warping function, which indicates that subject 1 progresses more slowly than subject 2. After temporal alignment, their latent trajectories over the internal time look similar. Now let's consider subjects 3 and 4, those two blue lines. Their observed trajectories look similar. The warping functions indicate that their progressing rates are different. After temporal alignment, their latent trajectories look less similar. Subject 4 starts at a more severe initial state than subject 3 and progresses more slowly, but reaches severe disease earlier due to time distortion. The key takeaway here is that after temporal alignment, the latent progressing trajectories can be described by the shared ODE system with different initial conditions. For estimations, real-world data is observed and discrete observational time points may be irregular across subjects. Observed data from NID subjects are denoted as OIs, including observed measurements YIs, the observational time points TIs. Here, MI is the number of observations for subject I. TI star is the time of occurrence of an external event, and covariates XI. Let's data denote the parameters including mu0 sigma 0, which are ODE initial condition parameters. F1 and F2, the ODE progressing mechanisms, and sigma, the variance of random error. Time warping function HIs are non-parametric functions. They are also of our interest. Estimation of theta and HIs is challenging because our likelihood function is intractable due to the unknown initial conditions and the nonlinearity in the ODE system. So first, we suppose the registration functions HI inverse are known. This is the log likelihood function. Because initial conditions are unknown and parameterized by latent variables E0, the relationship between initial conditions and E0 are in this form. We must integrate E0 out, which leads to a high-dimensional integral within the likelihood function. Unfortunately, this integral does not have a closed form expression, so directly maximize the log likelihood is intractable. Therefore, we consider a variational approximation approach to approximate the log likelihood function. The key idea of variational inference is to introduce a variational distribution Q to approximate the posterior distributions of latent variables. We rewrite the log likelihood function by multiplying and dividing by Q and applied adjacencies inequality. This yields a lower bound, which is known as evidence lower bound elbow. Instead of maximizing the original log likelihood, we will maximize the tractable lower bound to obtain parameters theta and variational parameters. Here, Q is the variational distribution for approximating the likelihood. Traditional EM algorithm is a special case of variational inference. In the E step, Q is the posterior distribution of latent variables. Unfortunately, in our case, the posterior distribution is intractable. Therefore, we approximate it by choosing a parametric family. Specifically, we choose Q from normal distribution with mean mu EI and covariance sigma EI. The variational parameters are denoted as phi, where each element phi I includes mu EI and sigma EI. We can further decompose elbow into two components. The first term is the expected conditional log likelihood of observed data under variational distribution Q. It encourages data fit. And the second term is the KL divergence between the variational distribution Q and the prior distribution P. It penalizes the deviation from prior distribution. We will optimize both terms to obtain theta and variational parameters phi. More specifically, to compute the first term, the expected log likelihood, for each given theta, we sample EI0 from variational distribution Q and transform to the initial condition eta I0. Then we solve ODE numerically using the internal time tau to obtain the latent disease trajectory eta. And we evaluate the contribution of likelihood. The KL term has a closed form expression for Gaussian distribution. Therefore, our full objective is differentiable, and we jointly optimize theta and phi while gradient methods. So far, we assume the registration functions are known. In practice, we need to estimate them. To model the unknown monotone registration functions, we consider a B-spline basis expansion. Here, SR is a vector of B-spline basis of order R with equal space interior knots. L is the number of interior knots, and AIs are B-spline coefficients. They are covariate-dependent. To ensure registration functions are monotonely increasing and satisfy the boundary conditions, we impose constraints on AIs. The AIs lie between 0 and 1 in an increasing order. We approximate the B-spline coefficients AIs by a neural network. We set the first coefficient AI0 to be 0, and the remaining coefficients as cumulative sum of the output of a D+1 layer neural network with sigmoid activation function as the last layer. The last layer uses sigmoid activation function guarantees that the output is between 0 and 1. By taking a cumulative sum, we ensure that AIs are monotonely increasing. With the estimated registration function, we evaluate the conditional log likelihood using the internal time tau hat. We adapt the forward-backward algorithm commonly implemented in fatty neural nets. In the forward pass, covariates X and observation time T are mapped into internal time or register time tau by neural network for time warping. We sample initial condition eta 0 by variational distribution. The register time and initial conditions eta 0 are fed into ODE solver to obtain latent disease trajectory eta. For ODE, if the functional form is known, we use a parametric ODE. If the functional form is unknown, we use a neural ODE and compute the elbow. In the backward path, gradients propagate through the entire pipeline, from elbow to ODE solver and to the neural network for time warping. We jointly optimize warping network, ODE parameters, and variational parameters through a single elbow function. Once we estimate our model parameters, we can predict patient trajectories and evaluate treatment effects. First, we map ongoing observations to internal time by using estimated registration function. Then we re-estimate the subject-specific initial condition by maximizing the conditional likelihood while keeping other parameters fixed. Then we integrate the ODE forward in internal time beyond the last observation to obtain the latent disease trajectory eta. Lastly, we map predictions back to observed time. To make decision on whether we should initiate intervention, we can compare treated versus untreated predicted trajectories or use predefined clinical threshold based on expert knowledge. We have established the consistency and convergence rate for parametric ODE. First, under certain regularity conditions, our maximum variational likelihood estimator is consistent. Second, when the progressing parameter lies in an Euclidean space equipped with the Euclidean norm, we establish a convergence rate. Specifically, the estimation error of both theta and registration function H inverse is at the rate of 1 over Rn in probability. This rate depends on the smoothness of the profile variational likelihood and the convergence rate for the estimator of inverse warping function. Okay, we apply our method to Alzheimer's disease neuroimaging initiative, INBRE, which is a large longitudinal multi-site study to track AD progressing using clinical imaging, genetic, and biochemical biomarkers. Here, our goal is to model progressing of cognitive decline using 4 harmonized composite scores as longitudinal markers, including memory, executive function, language, and visual spatial function. In our analysis, we included about 2,000 subjects with more than 10,000 observations. We consider metformin as a progressing modifying intervention. Studies have shown that metformin may reduce the risk of cognitive decline by lowering oxidative stress and inflammation, and reducing amyloid beta production, which is a protein of AD. Metformin may also improve cognitive function by positively modulating the gut microbiome. So we focus on the metformin in this analysis. For time warping, we include several covariates, such as baseline age, sex, APOE4 status, and years of education. To implement our methods, first, for the inverse swapping function, the registration functions, we use a neural network which contains 3 layers, 20 units in each hidden layer. And the activation function is ReLU, which is commonly used. To estimate F1 and F2, we considered both neural ODE and parametric ODE. The neural ODE provides better flexibility as the underlying disease trajectory is unknown. And the architecture of the neural network is similar to the network used for the inverse swapping functions. For parametric ODE, it provides better interpretability. Here we consider a ODE system given by 2 linear ODEs. Before the treatment, it is governed by F1. Here, A is the coefficient matrix, which captures the interactions among markers before the treatment. And after treatment, the dynamics switch to F2. B is also a coefficient matrix which captures the interactions among biomarkers after treatment. And the gamma is a consistent treatment effect that applied after intervention. We use Endem optimizer for stochastic optimization. We set the learning rate as 0.01, and we use early stopping and mini-batch training. We split our data into 80% as training set and the remaining 20% as validation set. Here I will show you the results from neural ODE. This figure illustrates the disease progressing for 3 example subjects across those 4 quantitative markers. Each row corresponds to 1 subject. The x-axis is register time, and the y-axis represents the observed measurements. Dotted lines correspond to observed measurements, and the solid lines represent our fitted trajectories. Orange lines correspond to progressing before treatment. Blue lines correspond to progressing after treatment. Over all the 4 markers, we observe a declining trend. Although the rates of decline differ across markers and subjects, our fitted trajectories closely track the observed data during both the untreated period and the treated period, indicating that our model can capture the underlying disease progressing patterns well. For comparison, we also include counterfactual predictions, assuming the first 2 subjects had not received treatment. So, which are represented by the red lines. As we can see that the model with treatment, the blue line, fits the observed data better compared to the model without treatment. In addition, for the first 2 subjects, after treatment, the treated trajectories show a slower rate of decline, which suggests that metformin may provide a protective effect. Our model performance is further validated by strong correlations between the observed and fitted cognitive markers. 0.95 for memory, 0.88 for executive function, 0.9 for language, and 0.75 for visual spatial function. To examine the effect of time warping, we plot the observed trajectories against the calendar age and the transformed age. The left panel shows the plot against the calendar age, centered and mean baseline age, which shows substantial horizontal variability, while the right panel plot against transform age, which is defined as the difference between register age and the calendar age. This transformation is motivated by the concept of biological age acceleration. It shows better alignment across subjects. Here I present the fitted registration functions of all the individuals in ENDLI. We can see that different individuals have different progressing rates and different stages of the disease. More specifically, cognitive decline is more rapid in females than males. For example, the median follow-up of 7.6 years correspond to internal time of 0.576 for females, which is 24% faster than males, 0.465. This result is consistent with existing literature that higher relative risk of AD in women than men. Similarly, we found ApoE allele carriers progresses 7.5% faster than non-carriers. Therefore, these results suggest that we should pay more attention and target care on women, especially for those with ApoE allele carriers, because they are at a higher risk of rapid cognitive decline. For the treatment effect, we report the proportion of individuals with a positive treatment effect and the conditional average treatment effect by their initial severity. We divide subjects into 3 subgroups according to their initial severity: mild, moderate, or severe. These results suggest that metformin is not uniformly effective for all the individuals in ENDLI. Specifically, in terms of memory, when the initial severity is mild or moderate, about 40% of subjects show a positive treatment effect, and none with the positive conditional average treatment effect. However, when the initial severity is severe, only 20% of individuals show a positive treatment effect, and the conditional average treatment effect is negative. Similarly, for executive function, there are about 50% of subjects with mild initial condition show a positive treatment effect. However, there are only 50% of subjects with severe initial severity show a positive treatment effect. These results may suggest that metformin may be more beneficial for individuals with mild or moderate initial severity than those with severe initial severity. So to summarize, in this work, we propose an ODE dynamic system with temporal registration and random conditions, initial conditions, to model AD progressing and treatment effects. Our temporal registration functions are covariate-dependent. Therefore, we can quantify how individual characteristics contribute to disease progressing. The random initial conditions allow that individuals have different starting points of the disease trajectories, and they are subject-specific. Besides that, our model can handle missing data and allow irregular visits. There are several directions for future work. Here, we assume a single shift after receiving the intervention. we can consider time-varying effects to evaluate the long-term impact of interventions. If the treatment is continuous, we can consider continuous treatment as an external variable in the ODE system. For example, a controlled differential equation to capture those response relationships. We can also integrate the clinical data with other modalities, such as neuroimaging data and CSF biomarkers. Lastly, we can also evaluate other types of treatments in real-world data. Here are the references included in this talk. And in the end, I will acknowledge my collaborators. Dr. Ze Xicai, he graduated recently. He is now an assistant professor at the University of Macau. Dr. Yuanjia Wang, she is a professor at Columbia University. And this work is supported by several NIH grants. Thank you for your attention, and I'm happy to take any questions.
Thank you, Dr. J. Questions from the audience?
So, Shanghong, I just want to get some better idea about because you use ODE system. And any other existing statistical model comparatively can do very similar thing. Can you give some kind of long description on that?
Sorry, I can't hear you exactly.
Dr. Zhang, do you want to type into the chat the question you just asked?
Yeah, so the okay, let me go back to here. Yeah, so for disease progressing model, one traditional approach is the sigmoid model. But the limitation is that first the model, the trajectory for each marker separately, they didn't account for any interactions among those markers. So if this is a dynamic system, if the value of one marker changed, we cannot evaluate how it affects other markers. So for this one, it's just analyzed for markers separately. And there are some other approaches like mixed effects model, which is used for longitudinal data. But the great thing about ODE is that it is generative model. Once we know the parameters, then we can simulate the disease trajectories and different progressing scenarios. So, for example, you can define the timing. When should I initiate the intervention? Then the trajectories will be different. So, such as this figure, if you initiate the intervention at different timing, the trajectory will be different. We can compare those trajectories and decide when is the appropriate timing to initiate the treatment. That's one of key advantage of the ODE. Yeah, so it's a generative models. Thank you.
I'm curious I have a quick question. So with Alzheimer's, one of the challenges with Alzheimer's has always been temporality in terms of what came first or what impacts first. and you have all these confounders that occur. And
Yeah.
because people don't use health systems the same way, we can't really go back using secondary data to track that. How does this help account for that?
So here, first we assume an underlying latent disease trajectories. So for example, this one. So we assume every subject share the same internal timeline, and our observation is just a sub-interval. So for each subject, this is just a sub-interval, not the full trajectories. And also in our model, so you can change. So for example, I'm interested in how the amyloid accumulation influence the glucose metabolism. Then I can change the value of amyloid glucose and put inside our model, fitted model. Then we can know how the glucose mechanism can be changed.
Okay.
Yeah, thank you for the question.
And were this built based on some standard or some ground truth, or where's that coming from? Because variability would be different across different groups. And there's some groups who are not even in the health system.
Yeah, it's a great question. At first, those ODEs have been used for model the disease progressing for ADs. And here, so we try to capture the subject variabilities. One is according to the covariates. Okay, let me go back to here. Yeah. So one is about the subject heterogeneity according to, for example, their genetic variation, environmental factors, and so on. Another one is to account for the temporal heterogeneity because they can start at different ages. So it means that they enter this study and different stages of the disease. Therefore, their calendar age actually may not represent the true biological age. So we try to accommodate the temporal heterogeneity in the time shifts where they progress at different rates, which correspond to the time in expansion or contraction.
Sorry to keep asking other questions also around this, because this is fascinating. Right now in the neuroimaging space, there's a discussion about brain age and chronological age. And just curious about how to use this in that kind of assessment, especially knowing that some of those images will only occur once in a while, and we want to use it to project into the future. If this is going to work for that kind of um, research.
Yes, yeah. So although here we only use the clinical score, the quantitative scores here, but the idea and the conceptual idea is very similar if we are using neuroimaging data. Okay, let me go back to this one. Right, so for this one, we plot the observed trajectories against the left panel shows against the calendar age, while the right panel shows the transform age, which we also call as like axis age, the difference between our register age and the calendar age. This is the concept of biological age acceleration. As you can see here, if we plot against the calendar age, there are substantial horizontal variability. We cannot align those subjects well. But if we plot against this transform age, those trajectories are more aligned. So it's better to compare those subjects. So another thing you mentioned about for neuroimaging data, we didn't observe like the full trajectory. So in this method, we can accommodate incomplete observations. The reason is that for ODE, we can still integrate ODE beyond even we don't have observations. So that's a great thing. We model the latent variables and we can do the ODE integration move forward. Even we don't have that data. So with the estimated parameters, here. So with the estimated parameters, we can integrate the ODE forward beyond the observed time.
Okay.
Yeah, thank you.
Any other questions from the audience? Okay, hearing none, I want to say thank you so much for sharing this wealth of information and presenting it and making it look so simple. It's not simple, but making it look so simple and easy to understand. So thank you so much. We appreciate you. And to everyone, thank you for coming. Our next presentation will be March 26th. We'll send the information out and we'll put that out on the INBRE website. So please keep watching. And if you have any consults or questions for the data science core, please again go to the INBRE website and put in a consult request, and we'll have someone reach out to you to follow up to see how we can help you. Otherwise, with that, I want to say thank you all for coming and have a wonderful weekend.
Yeah, thank you, Becky and Jaja, and thank you, everyone.
Thank you.